At the upper limits of the periodic table, the strong nuclear force struggles to hold itself together against the sheer repulsive power of packed protons. Across the entire universe, there are exactly 251 stable atomic configurations. That list ends abruptly at lead-208. Any element with a mass heavier than lead-208 cannot maintain permanent structural integrity. To survive, it has to shed mass. This structural failure does not happen as a random explosion. It follows a strictly governed deterministic sequence called a radioactive decay chain. To navigate this chain, the unstable nucleus relies on two primary mechanisms of ejection, alpha decay and beta decay. By mapping the rigid mathematical taxonomy of these ejections, constructing kinetic models of their rates, and observing exactly where those models break down in nature, we can track planetary-scale processes occurring miles beneath the surface of the ocean. This animation illustrates an alpha decay. By ejecting a helium nucleus, consisting of 2 protons and 2 neutrons, the parent atom subtracts exactly 4 from its total atomic mass number. A beta decay operates differently. The atom converts a neutron into a proton and ejects an electron. This changes the chemical identity of the element, but the total mass change is mathematically locked at 0. Because the mass of an isotope only ever decreases by exactly 4 or by 0, we can apply a simple arithmetic rule, modulo 4. If you divide any isotope's atomic mass by 4, the remainder will remain constant throughout its entire multi-million-year lifespan. This absolute mathematical constraint dictates that all heavy radioactive decay divides into 4, and only 4, non-overlapping taxonomic series. These pathways are classified by their mass remainder: the 4N thorium series, the 4N plus 1 neptunium series, the 4N plus 2 uranium series, and the 4N plus 3 actinium series. An isotope cannot jump between these tracks. From the moment it is forged in a stellar event, its physical destiny is mathematically sealed by the modulo 4 rule. Let's examine the mechanics of the 4N plus 2 series, which begins with its long-lived primary parent, uranium-238. This chart maps the complete physical pathway of uranium-238 across the atomic spectrum, tracking the number of neutrons against the atomic number. The structural toll of this journey is immense. To reach stability, the uranium atom must execute 14 major subatomic steps, ejecting a total of 8 alpha particles and 6 beta particles. The final destination for every atom in this specific chain is the stable isotope lead-206. Here we see the specific decay node for bismuth-212. While the ultimate destination of lead-206 is deterministic, the immediate path contains probabilistic branches. Bismuth-212 has a 64% probability of undergoing beta decay and a 36% probability of undergoing alpha decay. Mapping the physical route down the periodic table is only the first half of the problem. To utilize this process as a tool, we must calculate the precise rate of flow through this nuclear cascade. In a 14-step chain, predicting the total mass at the end is straightforward, but calculating the exact concentration of a transient daughter isotope halfway down the line at any given moment requires a kinetic model. Physicists calculate this using the Bateman equations, a system of linear differential equations where a specific isotope's rate of change is equal to its production rate from the parent above it minus its own radioactive decay rate. This diagram uses a hydrodynamic analogy to visualize these differential equations. The massive upper reservoir represents the long-lived parent isotope. It contains an enormous volume of material, steadily pouring into the system. The lower buckets represent the intermediate daughter isotopes. They are in a constant state of flux, simultaneously being filled by the radioactive decay of the bucket above them and draining out through their own decay into the bucket below them. This principle of fluid dynamics mirrors the sequential decay of atomic nuclei. Given enough time, this system will eventually settle into a steady rhythm. That steady rhythm is called secular equilibrium. For a decay chain to reach this state, the parent isotope at the top of the chain must have a half-life vastly longer than any of its subsequent daughter products. Uranium-238 possesses a half-life of 4.47 billion years, while its intermediate daughters decay in a matter of days, minutes, or milliseconds. It perfectly satisfies this requirement. Looking at this logarithmic plot of isotope activity over time, the blue line representing the daughter isotope rises steadily until it perfectly intersects the red line of the parent. At this precise intersection, the production rate down the entire chain strictly matches the decay rate. The radioactivities of the parent and all daughter isotopes equalize. In a closed system, like an undisturbed piece of continental crust, the radioactivity of uranium-238 will perfectly equal the activity of thorium-234, which equals the activity of radium-226. As long as the system remains closed to outside chemical forces, the entire 14-step cascade operates as a perfectly balanced perpetual kinetic clock. But the Earth is rarely a closed system. When the environment violently rips a parent and a daughter isotope apart, the mathematical balance of secular equilibrium shatters. Along the mid-ocean ridges, deep-sea hydrothermal vents eject dark, high-temperature plumes of mineral-rich particles into the surrounding frigid seawater. At this depth, uranium acts as a highly soluble element. It easily remains dissolved in the ocean water, unaffected by the physical debris of the vent. Conversely, its immediate daughter isotope, thorium-234, is highly particle reactive. This means it has an intense chemical propensity to adsorb or bind to solid surfaces. As the hydrothermal vent ejects iron and manganese particles, the dissolved thorium-234 instantly adsorbs onto them and sinks toward the seafloor. Its uranium parent is left suspended in the water column above. This differential chemical reactivity physically separates the atoms. It breaks secular equilibrium, creating a state of disequilibrium where the daughter's radioactive activity in the water no longer matches its parents. Oceanographers actively hunt for this exact state of disequilibrium. This animated graph tracks the ratio of thorium-234 to uranium-238. In a closed system, it's locked at 1.0. Dropping below 1.0 leaves a deficit curve, proving hydrothermal scavenging removes thorium. With thorium-234's strict 24-day half-life, this deficit area becomes a precise ticking clock. By utilizing the Bateman equations we established earlier, international marine projects like GeoTraces translate this radioactive deficit into exact physical measurements, calculating exactly how fast and how far these hydrothermal particles sink. By understanding the rigid mathematical taxonomy of decay and the kinetics of equilibrium, we transform the structural failure of an unstable subatomic nucleus into the ultimate chronometer for Earth's most inaccessible ecosystems.